At this point, we have a sufficient background understanding of the mesh current technique, and we're ready to look at an actual circuit and how we can perform those steps for our mesh analysis that we described in a previous video. For now, we're going to stick with this simple circuit which just has variables R1, R2, R3, V1, and V2, and in later videos, of course, we're going to look at circuits that have numerical values for resistances, voltages, and currents. And you'll notice that I have my mesh currents defined in a clockwise direction according to convention. As I've mentioned previously, that's not necessary, and again in a later video we'll look at an example where we see how we deal with that if we switch the convention on one of those current directions. Another thing that I'm going to note is that I'm going to define voltage polarities here in a second, and I'm also going to define those in this video according to convention. But in the next video, we're going to take a closer look at that, and we're going to see that really you have the freedom to define voltages in whatever orientation you want. But for now, we're going to look at conventional polarities for our Mesh 1 analysis. And so what that means is, of course, we talked about as we're doing this, our first step was to define our mesh currents. In this case, I have that defined where we previously did that. The next step is to apply KVL around each of our meshes and use Ohm's law. So if we're applying KVL, of course, we're talking about summing voltages. So I can come in here and I can define voltages across each of my resistors. And again, right now we're looking at mesh 1. So we're going to focus on one mesh at a time. So I have VA defined across resistor R1, and I can define VB across resistor R3. And so note in both of these cases, this current I1 is going through a voltage drop. And so again, that's sort of the convention, but what we're going to see in the next video is we don't necessarily need to follow that. So let's go ahead and jump into our mesh 1 analysis then. So oftentimes I like to just write mesh 1 so we know it's very clear if somebody else is looking at your work what you're doing. And so again, we're applying KVL, Kirchhoff's voltage law, so we can start at any point in this loop here. So let's say we start here. We can also go in either direction. We can go clockwise or counterclockwise. Just to match the notes, I'm going to go in a clockwise direction. We end where we start to make a loop, of course, and we're just setting the sum of those voltages equal to 0. So first we go through this voltage source V1. Note that we're hitting that negative terminal first, so that's going to be a negative V1. Next, we're going through this voltage VA. We hit the positive terminal first, so that's going to be plus VA. And then finally, we go through this voltage VB. Again, we're hitting that positive terminal first, so we say plus VB. We're back where we started, so we can set that equal to 0. So this would be our first step where we are applying KVL, or rather the first part of that second step where we're actually applying KVL. Now, the next step is we want to use Ohm's law to relate these voltages VA and VB to our mesh currents. And so what I'm going to do is I'm going to go ahead and move this V1 over to the other side so that I can say V1 is equal to, and now for our VA, if we look at this resistor here, we can use Ohm's law, and of course we know V equals IR, so that voltage is going to be I1 times R1. So I1 times R1 is equal to VA. And something that we're going to touch on a little bit more later is we do want to always consider our passive sign convention when we're using Ohm's law, or really any equation that relates current and voltage. In this case, our current I1 is, as we noted earlier, going through a voltage drop. It's going from positive to minus. Therefore, we use a positive sign in any equations that relate our voltage and current, such as Ohm's law. And so we can see that here because we have an implicit positive sign out front of that I1 R1. Okay, so now we're moving on to this VB term. So again, we have plus VB, and this one's a little bit different because notice that we have our mesh current I1 flowing in this side, but we also have our mesh current I2, and we don't want to neglect that. So we have to consider the net current flowing in that resistor R3. And so it turns out that that's going to be I1 minus I2, and that is our net current. So net current in R3, and we multiply that by the resistance R3. Now, one thing to note there is we're using a negative sign, or not a negative sign, but rather we're subtracting I2 from I1, and so that's because we have these mesh currents in opposite directions. So I1, I2 are in opposite directions, and so that means we have to subtract one from the other. And what we're going to see in a later example is if we had both of them in the same direction, we would actually end up adding them. And again, we'll worry about that when we get to it. And so in this step, again, we've used Ohm's law. Okay, so from here what we can do is we can collect terms to clean this up a little bit to make our solution process a little easier later on. So we can just say V1 is equal to, and then we have I1, which is multiplied by R1 in the first term, and it's multiplied by R3 in the second term, and that's all of our I1 terms, and then we have a minus I2 times R3. So this would be sort of our equation 1, so sometimes I'll like to label these, so we could call this equation 1, and that's going to be useful as we go back to solve that. So one thing I'll note before we look at mesh 2 is, of course, we've gone through sort of several steps here to get to this final equation, which I've labeled as equation 1. As you become more comfortable with this method, you can actually skip some or all of these steps, and we'll talk about that in class a little bit later, but we could, by inspection, pretty easily, for this circuit at least, come directly to this equation here. But as you're starting, it can be helpful to explicitly define our voltage polarities and go through this whole process of KVL, Ohm's law, reducing the equation. Okay, so let's take a look at our mesh 2. So we've got this same circuit, of course, and let me just explicitly write here, we're going to use our conventional polarities for mesh 2 as well. So conventional polarities for mesh 2. And so, of course, mesh 2 is over here on the right. So let's go ahead and define some voltages the same way we did for mesh 1. So, of course, we see that our I2 is going through a voltage drop here if we define it like this, and let's call that VC. And now we notice that we're going to have to define this polarity a little bit different for our resistor R3, and I'm going to move that to the other side. And we're going to have a plus on the bottom and a minus on the top, and let's call that V sub D. And so again, we've defined this such that our I2 is going through a drop and a drop, but we notice that our VD has opposite polarity of the VB that we defined up here. And so we're going to come back and we're going to talk about that in detail in the next video, but for now, let's just not worry about that and sort of take that at face value. So going through the same process that we did with mesh 1, we can say mesh 2, we are again starting with our KVL step. We can start at any point here and go in any direction. Just to be consistent with the notes, it looks like I've started in this corner here and gone in a clockwise direction around this loop, but you can start at any point, go in either direction, and you should get the same result. So starting at that point, first we go through V2. We notice that we hit the positive sign first, so we have a positive V2. We next go through VD, and again we hit the positive sign first, so we have plus VD. And then finally we go through VC, again hitting the positive side first, so we have plus VC. We're back where we started, so we set that equal to 0. And again, this is our KVL step. Our second step is, of course, to use Ohm's law to convert these voltages VD and VC into, or not convert them, but relate them to our mesh currents. So just like with last time, I'm going to move this V2 to the other side. So we can say minus V2 is equal to, and now for our VD, we have this same, not issue, but same condition where we have our I2 going in one direction, our I1 going in the other direction. And so we're going to have a difference of the two currents. We want to look at the net current through that resistor. In this case, because our VD is defined with that positive polarity at the bottom, the positive current that is being subtracted from is going to be our I2. So we can say I2 minus I1 times that resistance of R3. And so again, this is going to be our net current. And so an easy way to sort of double check yourself is if we're writing an equation in mesh 2 and we've defined everything based on the conventions, our I2 term should always be positive. Similarly up here, if we're talking about mesh 1 and everything's defined based on the convention, all of our I1 terms should be positive. So that's sort of a quick way to double check yourself. Okay, so that's our VD term, and then for our VC term, it just has the one current, so it's a little bit simpler. It's just going to be I2 times R2. And again, that's using Ohm's law. Okay, and then the final step is just to collect those terms. So we have minus V2, and we can collect we just have the one I1 term, so negative I1 times R3. We have two I2 terms, so that's going to be I2 times the quantity of R2 plus R3. And again, in class, we'll talk about ways that we can immediately jump to this later equation once you're more comfortable with the method. And we can define this as equation 2. So now at this point, let's say we knew our R values, so assuming we had a circuit where we knew our R and V values, we have two equations, two unknowns, which means that we can solve for those mesh currents. And so, as we've talked about in a previous video, there are several different methods we can do. I'm encouraging you guys to get more comfortable with the matrix method because that's going to scale up nicely as we look at more complicated circuits. But in this simple case, we could also use linear combination or substitution. We could also use MATLAB to solve this in terms of variables. So if that's something you're interested in, let me know. We can go over that, but that's not something we're going to be worried about a lot in this course. So one last thing to note here is that if we weren't using mesh current method or node voltage method, we would have needed three equations. So let's say without node voltage or mesh current methods, we would need three equations. And so maybe you've done similar analysis on a circuit in Applied Electrical Theory 1. And what that would have looked like is we would have needed two KVL equations, one KVL equation in each loop, or one KVL equation on one side and one KVL equation on the outer loop, either way, as well as a KCL equation at one of these two nodes. And so we can see with the mesh current, it simplified that a little bit. We only needed two equations. So let's come down here and we can just annotate this. We can say with our mesh current, we saw we just needed two equations. And so actually in this case, with our node voltage method, we would have just needed one equation. And so that's something we're going to come back to in a later video as well, is we're going to kind of look at a comparison between node voltage method and mesh current. And I'm going to try to give some pointers on when is one method more convenient. And in a lot of cases, it's just going to come down to your personal preference.